have to still get permission. But like, all you do is say like their university, and then yeah, ShapeNet core. Yep. Yeah, so you'll have to just fill this out, but they'll give you access in like 2 or 3 days, and then yeah, you get the OBJ files based on a lot of license.
Okay. Do you know this texture?
Yeah, they have texture files as well. They have NTR file as well as the associated JPEG or PNGs for the texture.
Okay. Yeah. Okay. I'll probably use that then. Hopefully this doesn't too much. But yeah.
This is actually really cool. Okay, so once you get the OBJ files in a couple of days, I'd like to see this recruit and see if the images actually consistent.
Yeah.
So if those are good.
Alright, sounds good.
Nice. Good job.
Yeah. I think I'll probably need like a week.
Yes.
Or like multiple weeks.
Just still waiting on the server. So.
Yeah. The server's kind of slow.
Okay. Yeah.
Is homework 4 released soon, or?
I published the draft today, and I'll still massage it. And you're getting a triangulated mesh, and you want to render it, and you also have a mirror in the scene, so you want to show it. And along the way, this triangulated mesh, you need to apply all the shading effects on it that we had. And maybe I'll throw in also some billboards and pictures so you can play with texture a bit more, maybe. I'll decide, but actually if you think about it, the mirror already includes a texture, so maybe I don't need, but the mirror will be the headache. Other than that, it's very classical project. and it needs to be in OpenGL. So everything that was forbidden before that, like say matrix rotate or project matrix or apply, everything now is OpenGL, is WebGL related, or whatever you find, OpenGL if you want, or any GLSL applications. But shaders must be there. It is CPU only will not work. And I was asked today, and I figured out that I had an error. When did we agree that the midterm is? Talked about it last meeting, but now I had a moment of sanity.
Did we say it was next week or 2 weeks? I don't remember, honestly.
So what I remember is that 26, which makes no sense because it's not a good day. And last meeting we said that it will be next a week from today, which makes sense to me. But if somebody is screaming now that it's stepping on some deadline, let me. Make sense to everybody? Okay, so formal midterm is next Wednesday. Very good. And today, basically, quadries, maybe I remember a bit about where shaders together. We finished our last meeting talking about hash, geometric hashing. I have one predetermined distance that I said I want to know who lives in the distance. Points, it needs to be points. It can work in 2D, 3D, any fixed dimension. It will not be found in the dimension. And the geometric hashing, we said we basically have a grid all in the same cell size, and I want to know, say, for the red grid cell or radius of 1 of 1, who lives in this grid cell, because I just landed here, or I just had a ray that entered to this one when I'm doing ray tracing, and I want to know who are these points, and hopefully the number of such points, data points, that lives in this grid cell is small enough so I can check all of them in a constant time. For example, if you think about players, and Minecraft player has some size in them, you cannot compress them too much, so there will be such grid cells, not too many nodes, so even if you need to check each one specifically and see which one do you see, you're fine. And if you are worried that your query point is just near the boundary, then probably you want to perform similar query into the hash table with the nearby cells, the 8 nearby cells. And then everybody who is distance 1 from you, you cover. Now, in 3D, everything is absolutely the same, but this time checking the 8 just the 9 cells around me will not be enough. And in 3D, I will have to check the 27 cells out there, right? 3 by 3 by 3. And in higher dimension, things starts to be shaky because curse of dimensionality, very well-known term in algorithms in databases, that most things behave exponentially when as dependency in the dimension. And the geometric hashing, and the beauty is constant time on average, order 1, to see if the cell is empty or not. On average, your completely hashing is where you are putting your belief on the rules of dimensionality. There is no karma that works directly against you, and that's why the hash function, hash table will work perfectly fine. Let's talk about quadries. Show me hands if you know what are quadries, or if I taught you what are quadries. That was yes for the first and no for the second.
I think we did it in the algorithms course. But
We
maybe I'm
did probably. The same, and the rest of you don't know about quadries. Okay, Yeah, I'm quite obsessed about quadries. They are like the ultimate answer, 42. It's one data structure. You can have better data structures once you have one particular purpose in mind. If you tell me that's my only purpose, I can probably come up with a data structure that somehow, at least theoretically, will be better than quadries. But I have a lot of different applications, different queries, different graphic application even that I need for my data structure. I need to do ray shooting. I need to see who are the vertices that are near me. I need to see what are the rooms, what's the floor plan, and each one might require a separate data structure or use quadries, and it's doing most things on average very well, and it's very easy to change the program to adjust it because of the simplicity and some weaknesses of the theoretical part. Okay. So I'll define quadries on parts that you actually less important but much easier to explain. And I'll assume that I have an image that is bichromatic. I wanted to have colors that I can also use with a marker. That's why it's green and red. And quadries always defines on a range. I need to decide about the range, the size of the universe ahead of time. And I want the size of the universe to be power of 2. So at this moment, I have an image that starts, say, from 0 to 7. So age will be 3, 2 to the 3 is 8, 0 to 7, and 0 to 7 on this image. And let's say that, as I said, my image is bichromatic, and I want to have a data structure that can support various queries, like I want to find one particular point out there, and I want to know if this point is a green pixel or a red pixel. That's not very complicated, but that's also way overkilling with a quadry. Just keep the original input if you want. Bit harder. I'll give you a range, a query disk, and I want to know are all the points inside the disk are green, or how many red points and green points, green pixel, red pixels there are inside the disk, and so on. Or we talk about quadries for other type of data, and then I will ask, for example, what are the triangles that lives inside the query disk inside. If the data will become houses in the US, and I want to wonder, should I build Walmart right here, because here are how many people live in a radius of 5 miles, and I want a data structure that can very quickly tell me how many points or what's the nature of the data that lives inside this puzzle. So right now I want to, I'm back to the case of the bichromatic image, and I want to build a quadry that can answer queries like, and here is the rule. The data is given to you, you can meditate on it, image given to you, you can meditate, and then I'll surprise you by a query. And once I'll surprise you by a query, I need the quick answer, prompt answer. What is the answer to this query? Why do I need a quick answer, and why does it make sense to do it overall? Is because there are a lot of queries. It's not just, if I want to know what is the scenario with this disk, I'll just get the information from the raw data. But I have plenty of disks, or plenty of ways when I'm doing ray tracing. Plenty of different queries. That's why it makes sense to spend more time and effort in creating the database, the data structure, and that will be a bit slower, so that the time per query will be much faster. Okay. So we want to ask, are all the points inside each one of these query disks, are they both colors? Yes, for D3, not for the other disks. Okay. So I'll present a few data structures, and all of them are hierarchical, and they all have the same basic structure that we saw already in the binary space partition tree, which was we have for every node V, I'll refresh your memory. Here is my whole world, or my whole thing that I need to store, and I'm going to create a tree, and each node V in this tree is associated with a region, the kingdom, the range that V corresponds to. And basically, for every R of the root is a whole world, the whole region that I care for, the whole image that is in the input, and for every node V, for every node V in the tree, R of V is contained in R of parent of V. If I have two children, their region is included in my region. I'm sure it's part of my region for each one of my children. Of course, if you have a parent. If you're the root, then you don't have a parent, but then your kingdom is the whole plane. So let's see what's happening here. Here is the root of the quad trace that I generate for this image. Now it's bichromatic, but green and white. And what is the kingdom of the root? The whole input image, remember, just bichromatic, no gray level, just 0 and 1, the whole image level, all the time, from 0 all the way to the edge. And it will be, and in images it will be nice because pixels will have integer coordinates. We don't need to split a pixel. So every pixel will have integer coordinates. And with all quadries, I'll have to have some splitting policy. I need to decide based on the data, should a node V have children, or can I leave it as a leaf? So the splitting policy over here would be if the region of a node so if the splitting policy here will be, look at the region of a node. If the region of this node contains only pixels of one of the two colors, does not contain two pixels of two different colors, then I leave this node alone. I don't need to split it. It doesn't need to have children at all. Okay, so if my whole image would have been green, I will not split it at all, and I will have the root that is also the leaf, and that's the whole tree. And that's great, that's a very efficient tree. In this case, the root does both white and green pixels, so I need to split it. Now, the rule of quad trees will say, when you split it always at the middle. The size of each one of these quadrants, 4 quadrants, the edge length of each one of the quadrants is the same. no matter how the data is distributed. We see other trees that will try to balance somehow the height or try to optimize it. Quad trees, for simplicity, will say, if your input are the numbers 1, 2, 3, 4, 5, 6, 7, let's build a quad tree on these numbers. Here is R of the root are all the numbers from 0 to 7, and if I need to split the root, then the left child, its region is 0 to 3, and the right child, its region is 4 to 7. Both have the same number of pixels. That's in 1D, the same goes in 2D. Now, a node is either a leaf or has exactly 4 children. That's only 2 options, either a leaf or 4 children. And I pretty much described the whole tree. This image, I need to split the root. Now, when I split the root, I'll have, as we said, 4 children, and it's nice to call them the northwest child, the northeast, southwest, southeast child, or to label them as 0, 1, 2, 3. Here are the 4 children, and for each one of them, I'll basically repeat the same process. Here it is. The root needs to be split. What about the northwest child? Fully green. Does not need to be split. I leave it as a leaf. However, I need to tell you that everybody inside this leaf is green. That is, this whole quadrant is fully green. Southeast quadrant, fully green as well. Southwest, fully red. So the leaf needs to know this data. And what about the northeast quadrant? It has both red and green pixels. That's why I need to split it. And splitting again, like this on the same level. Split it exactly in the middle of the way. 4 quadrants, each one with the same edge length. This edge length equal to this edge length. And let's call them, because it's quadrant 1, let's call them quadrant 1, comma 0, 1, comma 1, 1, comma 2, 1, comma 3. It's not 13, it's 1, comma 3. You all heard about World War XI. 1, comma 0, 1, 2, 3. And from which fully green, fully red, and these quadrants need to be split once again. Okay, and so V northwest, dot, 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 V southeast. And you can continue recursively. And you can build this tree either top down or bottom up from the, you can start from individual pixel and start merging them. What's the height of the tree? What's the maximum height of the tree? Well, I start when it's 2 to the edge, say edge is 10, 20, 30. 2 to the edge. Each time, what happens to edge? Each division, edge is decreased by 1. I divide by 2. It's tempting to think about it as divide by 4 because it's 4 children, but in the x coordinate, I split by 2 and split by 2 in the y. So the maximum height of this tree is age, this size of the universe that I start with, but it's quite misleading because if I want to, I'll give you a query point here, I'll give you a point x, y, and I want to ask, is this point x, y, is this red or green? Based on, and all you have is access to the root of the quadtree. What would you do? Give you x, y. I want to know if it is, if it lies in the red pixels or green pixels, or maybe not at all. So what are you doing?
So you just travel down the tree until you hit something that is not a parent anymore? Until you hit something that's just a leaf, I guess is what you do. I guess my confusion comes in each of the nodes, at least in this example, they specifically only hold like spatial information, but they don't have any information about the pixels, right? Are there other instances where the content of the nodes isn't variables that describe like
Yes.
spatial information? Okay.
Yes, absolutely. Here I don't need, but, and actually the node doesn't need to do anything beside existing. Let's understand what am I trying to say about it. Look at this case. Here is, I'll tell you that here is the root. That's a pointer to the left child, a pointer to the right child. And I'll give you a query point. What should I do with this query point? I first check if my query point is somewhere outside it. I need to say the whole quadtree lies on the point from 0 till 7. So if Q would be 9, we already said 8. I have no data, it's outside of my world. But if it is, do I need to store at the node the range that this node corresponds to? It's one of the elegant and quick ways of why quadtrees are so popular. The question is, does the node need to know about the range it corresponds to? Let's think about it, but let's consider it. If you just give me a node of the tree, absolutely, I have no clue what is the range of this tree unless it's specified. But if I don't, but I start from the root of the tree, Q equals 7, what should I decide? It's, look at the root. If the root is a leaf, you're done. It's because it's 0 to 7, so if the root is, it means it's either fully green or fully red, you're done. It's not a leaf, so you need to branch. Branch would be based on what? Compute where do I split, because I don't change the splitting. That's where I take advantage, as the splitting is exactly in the middle. So, yeah, you got it. You just based on the value of Q, you know where to go to the left and the right, and of course you know what are these nodes. And had this node have children, could have continued as well. Let's see even a cooler part. So that would be 0, that would be 1. Let's say that my data consists of the points 0, 1, and 7. That, let's say, are the only pixels that I have any information. And and my query is I also want 6. 6 is also in my data. And my query is indeed 6. Can I just look at the number and describe what is a path that leads to it? In the sense of when I'm going from the root to the leaf, assuming that I'm going all the way down to the leaf, that the leaf are singleton, unique pixels, let's say. Then what happened to my path? I branch right on my way to 6, I branch right again, and then I branch left. Right, right, and left. On your way to 6. 7 would be right, right, right. Can you describe this path without looking at the tree at all? There is something that makes cs3 very attractive, actually.
Is it you would convert 6 into binary and then that would give you.
Let's see if I can do it, which is 1, 1, 0. In binary, that's 6. Everybody agree? So if I understand that 1 in binary implies go right, and go left. And voila, you have the whole description based on just the bits, single bit. Quadrant 2D, you look at 1 bit and X and 1 bit and Y, and if you have 4 children, it tells you which one of the 4 children you have, based on only 2 bits. How do you get the value of a single bit? Everybody needs to know it, but maybe you don't. How do I get the value of it? Yeah.
You can do a bitwise and.
Bitwise and
the power
1%, yeah. Yeah.
So
you
the reason, sorry, so like this works because we're using the representation in binary from 0 like onward, right? This is specifically because of the way we've set up the numbers we're using. But in other cases, would you need to store the center of, like a center of your root to determine your splitting?
No, but what could happen is that here I had to separate pixels, which should be in different colors. What should I do if this node is already a leaf? Then I can start walking from the root downward until I hit to this leaf. But there is something cooler. If you think about the value as about the query point as a description of the path, I can take Q and I can hash Q. Put it in a hash table. Insert the hash value of Q if I'm going all the way down to Q. Now, what do I do for this leaf? I will hash only the number of 1, which is a path all the way to this leaf. And remember, that's a leaf that has 2, had I split it, it has 6 and 7. But I do store this leaf. What I don't have in the hash table is, are the value 6 and the value 7. Instead, I just have the value 1, 1. Why is this useful? Why do I want to use hash table in addition to the Q? Basically, I'm taking all the leaf and put them in the hash table. And now I want to find where is Q based on this path. It's a little tweak, little advance. Well, I can always start from the root and go all the way up to age. And age, remember, age is about log of the size of the world. But does anybody see a way to find the leaf?
Are we allowing like 2 6s, or is it like a set and we only care about existence?
I have a point Q. I want to know if Q is green or red, and for this I need to get to the leaf that contains Q. And somehow I argue that this hashing trick should somehow make things faster.
So could you just take it's like 1-1, hash it, and have the hash table point to that leaf? So then like you don't have to traverse the tree, you just hash it and then jump straight there. Is that what you're getting at, or?
Yes. So yes and no. If the leaf exists, it means that I can in constant time find it. Here the leaf does not exist. What do I do next? And let's schematize it. Here is my quad tree. Here is my path. I'll do it still in 2D. White, white, left, white, all the way to Q. That's if the whole path exists, and only Q is in the hash table. And I'll write Q as a list called sigma 1, sigma 0, sigma 1, sigma 2, sigma 3, sigma 4. You know, each one is a bit. And if you think about all the bits, then sure, you can just check in the hash table and maybe it is a leaf, Q is a leaf, and you just found it in constant time. But I want to get better time even if it's not, if Q is a leaf, but a bit higher.
So if it is a leaf, it has a parent using the first.
And just to make sure, there is always a leaf that contains Q. There's always a leaf that contains Q, but this leaf might be the root, it might be a single pixel, it might be anywhere in between.
So you can take the sequence of instructions up to the very last one. If it exists in the hash table, you can skip entries of the tree, I think is what you're saying. Like we have a Q, sigma, the sequence of sigmas. If you follow the most significant sigmas take you to the lowest layer of the tree. So if you've saved something previously, you can only go one more layer down the tree. I might be mincing my words a bit though.
So I checked if it is a leaf, and think about this path, pi, that leads to Q. I checked if Q is a leaf, if Q is a single pixel, that is, a leaf is fully constrained. Q by itself has a sequence of bits that represent the whole path to Q. But it can be that I shouldn't take from this whole path all the bits. It might be, like in this case, that I need to take only some number k of bits, but I don't know what is k. How many bits should I take to represent the path to the leaf that contains Q? Yeah, good.
Do you just divide by 2 and then check C?
Divide what by 2?
Divide the current number, the Q by 2, and then see if it exists in the hash table?
I think that you are onto something, but if I just divide Q by 2.
Which what is down there?
I mean, remember, you have the hash table. So far, I didn't justify why you want the hash table at all. And all I get from the hash table is a node exists as a leaf or does not exist as a leaf. And you know, I can actually, I should actually have in the tree all, I'll take it back. In the tree, I'll insert all, and actually insert to the hash all nodes of T. That is, in the case of these three, the ones that I'll insert to the hash are, let's use a different column. What do I have in this example? I have 0 and 1, so I have this node, and this node. And I have this node and this and this. And that's the only node that I have in the tree. And I hash each one of them, and the key for the hashing are the left, right, the path to them. Yeah.
So if you don't find it, could you just like chop a bit off and then rehash it, kind of just work back up the tree until you find like one of the nodes that does exist? Or I guess it's almost linear again, so.
Maybe,
You're almost there.
maybe you could.
You're almost there.
Maybe you could just chop half of it and make the runtime log of age.
Remember, if a node exists in the tree, then all its parents also exist in the tree. Absolutely. So my next attempt, I'll start with age, check if it exists. What should be the height that I'll try my next height? The height of this tree is age. My next height will be at age half. Check if there is a node exist on the path to Q. Because you know what is Q, just take the correct number of bits from Q and ask if it's existing on the hash or not. If I have a node on it and it's not a leaf, then now I know the Q is in the leaf that is somewhere between level age half and age. If I don't have even the node on the way to Q in level age half, no point of looking downward, just look upward and continue the binary search. So the time to answer a query will be, log of age, which is log of the size of the universe. How many pixels you have out there. Cool. No? It might be the first time that you see data structure with log query time. And by the way, this trick is also used in routers of kind of any prefix tree that's not in the context of algorithm of prefix trees. And there are special memories that routers like that can enable answering such queries really fast. Anyhow, so that's log. Okay. And remember, the maximum height is age. Once again, why? Because I assume that all my pixels have integer coordinates, and I have only, at most, the width would be 2 to the age, if I need it. So after age many edges, I'm getting to the size of every leaf. If I went down age levels, then the size of every leaf is 1 by 1. Okay, that's kind of compressing maybe with very questionable effectiveness for images, much better compression. But now let's move to the case that I have a set of data points. And I want to enable queries like, given a query point, is Q is in one of the data points or not. But I also want other type of queries that you'll see soon, like inside a range, who are the other players around me? And the data points, by the way, I don't insist that they have integer coordinates. It's not that important, but let's assume that the point, or that the data points have integer coordinates at the moment. And I'll still build a quadtree. And the splitting policy, and now I don't really have the columns. I just use them to highlight, to connect it to the previous example. And I need to tell you what is the splitting policy. And the splitting policy here and every other quadtrees will be split until the information inside a node is small, constant size. So for this example, to keep things elegant, let's decide that we are splitting as long as we have more than 2 data points in the range of it. That is, a node V, that's it, in my range I see 2 or more data points, I must have children. I need to split. If I see 1 or 0 child in my range, I'm perfectly fine. I don't need to split. I'll stay as a leaf. So, root, as always, corresponds to the whole plane. I have my data points A, B, C, D, E. The root is more than 1 data point, so splitting is still at the middle. Every quadrant at this level has the same size, the same edge length. So I split the root into 4 children, from which the northwest child, quadrant 0, says I see just 1 data point in my range. So all I need to do is to store this data point together with all the information associated with it, right? Maybe it's a vertex of a triangle. Maybe. I need to store all the information about A, including its exact location. I don't know where is A inside this quadrant, so A needs to know what is exactly its location. I cannot decide where is A, can deduce where is A, based on just the fact that it lies in this quadrant. Just gives me very bound. Okay, quadrant 2, southeast, fully empty. So I leave it as a leaf, or even remove it at all. Or a leaf with 0 nodes inside it. Either way, it's a leaf. Quadrant 3, southeast, needs to store the point D. And that's it. Doesn't need any other information, but needs a pointer or all the data about D itself. Northeast contains 3 points, so more than 1 point. Splitting policy, split always to 4 quadrants, all with the same size, from which quadrant 1, 0 is empty, quadrant 1, 1 contains C, 1, 3 is empty, and 1, 2 contains 2 points, need to split again. Quadrant 1, 2, 0, empty, 1, 2, 3, empty, and here are 2 quadrants that are not empty. So if they all have integer coordinates, then I know again that age is a maximum height. If they have float coordinates, you'll still use this quadrant. You just decide about some splitting policy, or just say that the height might be high, depending on what is a maximum size divided by what is a minimum size. If I have 2 points that are very, very close to each other, it could be that I need many levels. But there are variants of compressed quadries that says if I just have a child that has a grandparent and grandparent and grandparent, and all of them are very close to each other, there is a way to skip all the middle point. Everybody understand what I'm talking about? Here is my input. Here is the input range. Here is my 2 and the only point that I have in my data. Quadrant with no compression would look like, does the whole region contains more than 1 point? Yes, so I need to split it. Splitting always in the middle. KD trees that we'll mention later will try to be smarter about way do I split, but then the simplicity and the knowing what range is going away. It will not be as elegant or not be as quick to implement and as easy to debug. Quad trees will say I split at the middle, which means that I need to split in the middle again, and I need to split in the middle again until finally I succeeded to get them into different quadrants, and only then I can stop. Okay, and usually you'll do it, maybe not 1 point per quadrant is overachieving. You'll do it as long as you have simple information at every leaf, say no more than 17 points. Okay. Next, I have a query region, query disk. I want to know what are the points that this query disk contains. And pay attention, because all the search trees, all the spatial composition will work all in the same way. here is my query region, and it's much easier when the query region is axis parallel, axis aligned. I'll do it as a disk just because it's easier or on the eye in the slide. Easier to see whether that's a query, not to be confused with a quad. And I want to report, to print all the points that lies, all the data points that lies inside Q. What do? I go to the procedure report recursively. I'll start when V is the root of the quad tree. And Q is my query disk. And if V is null, doesn't have any points, obviously. If R of V is disjoint from Q, meaning that here is Q, R of V is somewhere far away. They don't have any points in common, and somehow something happens to R of V. R of V is the region of the node V that I called it, maybe the root itself, has nothing to do with Q. No points in the plane and definitely no data point in common. Maybe Q is somewhere around here. Then, of course, return no points is relevant for me. That would be one easy case. Other easy case is Q contains R of V. R of V is fully contained inside Q. What can I do in this case? In this case, I can say every point that is in the subtree of V, every data point that is in the subtree of V, subtree rooted at V, is also inside the query point, so you have to report it. You don't need any further checking. Just report all of them. For example, if Q is huge and it contains the whole data, the whole scene, report every point in the tree. Okay. What's next? If V is a leaf, might contain several points, 0 or 1 point, then I need to check each point that is inside this leaf. Let's say I ran into quad tree 0. I need to ask the points, the data points that are inside quad 1, 0, are they also inside the query disk? Because I cannot decide that that independent of where the data point is, it's also inside Q. I have to check specifically each point. If it's only 1 point in the list, then it's easy. If it's 17, it was 17, but that's why I wanted no more than 17 points per list to keep it very easy to check. Else, if nothing else seems to work, that is the expensive part, which means I could not, none of these cases work so far if Q is a root, if I start from the root and here is Q, there is none of these cases that is applied, so what do? Call yourself recursively on each one of the 4 quadrants. And that's the only thing that you could do. Make sense? And that would be the expensive. But it's fantastic filtering part, right? It means that I have a query that is relevant for the East Coast, data points, people that live on the West Coast will figure out that we don't need to visit this part of the quad tree at all. And it goes even better. If I would just want to know how many data points there are inside Q, not who are these data points, just how many, then here instead of print RV is fully inside Q, then instead of reporting all the points in the subtree of V, all I'll do is that every node V will store how many data points are inside its subtree. Make sense? So the root will say, I have 5 points in my whole quad tree. Quadrant 1 to 2 will say, I have 1 data point, and quadrant whom, and Other example. Every node just know how many data points it has. And then how do I change the report? Just say instead of report all the points, just take their number and sum up all these numbers every time that you see a quadrant that is fully contained inside the queue. Just ask how many points, but you don't need to go visit the list at all. You have a huge disk, contains all of Tucson, just ask how many people there are in Tucson and add it to the overall sum. I mentioned that it's much easier to do the query when the query region is axis parallel, and that's why. Here is Q and here is R of V. How do I know that Q is inside R of V? Check the X max and X min of both points. If Q contains R of V, if it contains the X projection, and it contains the Y projection. Right, and that's how you find if there are disjoints, that's how you find. But you are just looking at the X and Y values. Bringing me, by the way, to the midterm question. We talked about the perspective projection, and we talked about the projective distortion that changes, moves everything from the forced room into the canonical volume, -1 to 1. If I want to do a clipping, like I want to know which points or which triangles lives inside the forced room and which one are not, should I do it before or after the transformation? In terms of big O of complexity, the answer is that it doesn't matter very much. But in terms of actual running time, one way is clearly better. Here's my canonical forced room. Here is a point P that might be in the forced room or possibly is not in the forced room. How our projection distortion matrix, projection adjustment matrix works. Remember, it was invertible matrix. It changed the distances from P to the camera. I definitely changed the distances, played with my GeoGebra. I think that it explains quite nice. I mapped P into some other point. P was mapped into some other point, P prime, that might have higher or lower Z, but what was the main property of this matrix? Well, why did they do this whole gymnastic? They did the whole gymnastic because they want to use the GPU, the shaders, and to use the shaders and the GPU, it needs to assume that that everything lies in the canonical volume between -1 and 1, A, and B, you want to assume that you are using orthographic projection, which means that you take the XYZ and you just ignore the Z at all. But before you ignore it, you think about P and P1 that is mapped to another point, P1 prime over here. And what you guarantee is that if P1 was further away than P, then after the projection, they will also be further away, so your depth buffer is still alive. That is, you can still know what is closest to the viewer and what occludes what. And back to my question, I want to just decide if P is in the canonical forced room or not. Should I do it before or after the projection? Probably it wouldn't justify doing the whole projection immediately, but I need this matrix no matter what, so yeah.
I'd say doing it after, because then you guys check if the new point is it greater than +1 or less than -1, then you know it's out.
Exactly. So now if P is there when you have just an axis parallel box of -1 to 1, just ask for X separately, Y separately, Z separately. Z is actually not in the game, but you ask for X and Y, and you just check larger equal than the relevant X and Y. If you want to check if it's inside the original force room, now you need to check, is this underneath this line, this plane, because it's in 4D, and on the correct side of this plane, correct side of this plane, correct side of this plane, and so on. So it's the same operation, but it's more expensive than just ask for the smaller or larger. I need to ask how is this with respect to each one of the planes, which is constant, but we care about constants here. It's the same reason that I prefer to have my query, if possible, to be axis parallel. When it's axis parallel, I can completely subdivide the check. It is in the correct range in x, it is in the correct range of y, and only if the same true for x, y, and z, then I'll ask. And then these are 3 independent coordinates. And at each point, I just ask for this value of z, smaller or larger than 1. Don't need to multiply. To ask how is this with referred to a plane, I need to multiply by the plane. And many more, multiplication and addition. Finally, in the graphics, hardcore graphics. I have a set of triangles at the moment in the plane, still, and I want to ask to build a quadtree that can help me do the graphics operations, which include everything that we saw so far. Given the query disk, what are the triangles that it intersects, but I also want to do ray tracing. So first I need to tell you what's a splitting policy for a set of triangles, non-crossing triangles. Let's simplify. They can decide that they split a quadrant if this quadrant intersects more than one triangle. If a quadrant intersects 0 or 1 triangle, let it be. Look at the quadtree, the whole universe. It contains 4 triangles, A, B, C, D. 4 triangles. So I need to split it. Quadrant 0 asks how many triangles do you intersect? 1, so I don't need to split it, but I do need to point from this node to the parameters of this triangle because it intersects this quadrant. Okay, quadrant 2, don't intersect any input triangle, leave it as a leaf or don't make it exist at all. I don't really need this node. Quadrant D, similar to quadrant 0. So quadrant 3 needs to point to D. And quadrant 1 intersects several triangles, more than 1, so I need to split it. Of course, as usual, as before, probably I do it with 1, I'll do it as long as it's no more than small number of triangles. But here I'll fix to 1 triangle. So I need to split quadrant 1 and quadrant 1, 0 empty. 1, 1 contains C, and quadrant 1, 2 intersect 2 triangles, and when I'll keep on going, notice that 1 to 0 and 1 to 1 both intersect A, so A will be stored multiple times. So there is a wasteful something here maybe. Right? I'll have the same triangles that might be stored in multiple nodes. And if you think about the example with these 2 points that needs a lot of nodes in the quadtree, then I can exchange this example and make 2 segments instead of 2 nodes very close to each other, 2 triangles, and of course I'll have to split multiple times. You can decide about different stopping condition about when exactly do you want to stop. Okay, but that's quadtree for a set of triangles. How do I report all the triangles that intersect a query disk? Exactly the same code. But if your query disk contains a node, leaf or not a leaf, I don't care. Every triangle that intersects this node also intersects the query disk, because my query disk contains the whole node, so just report every triangle that is relevant to this node. If your query disk is far away from the node, from the region of the node, then get away from the report, otherwise continue. I might have a slide of it, but here's my board. I took a slide for it, but let's see what I Here's a way out that continues in this direction. I want to ask what is the first triangle that this way intersect? What is the first triangle that this way intersect? I find a node that contains the origin of the ray. That's where the camera is. Now I'm talking about ray tracing applications. We should have started here. Ray tracing application. Here is a camera. Here is one of the many rays that you generate, one per pixel. My ray lives in two. What do I do with this ray? I trace the ray from the quadrant where the ray was born until I exit this quadrant, and I see to which other quadrant of the tree, which sibling this way enters. And I figure out that in this case I'm exiting 2, but I'm entering into quadrant 3. From 2 to 3. Going to quadrant 3. The node of quadrant 3. Is this a leaf? Yes, in this case. Who lives inside this leaf? Oh, there is only D, because it's a leaf. It's very simple information. Great. Is my way intersect D? Yes, and that's the only triangle, and I'm done. Okay, and that's how I answer ray tracing. Let's take another example. What will be the scenario here? I want to eventually report that my ray hits B. What should I do? I start at quadrant 2, from which that's not very general. Let me move this way by tiny bit. Okay, just I don't want to go exactly through the corner. Just no typical case. From quadrant 2, I moved into quadrant 1. Is it a leaf? No. So inside quadrant 1, what is the first quadrant that my ray intersect? Answer, it's quadrant 1, 2. Where is 1, 2? Over here. Is it a leaf? No. What is the first sub-quadrant that my ray intersect inside quadrant 1, 2? It will be 1, 2, 1, 2, 2. 1, 2, 2. At which you realize that B lives here, and it is a leaf. So right now I'm back to the first mode of asking, is my ray intersect the triangle that lives in this quadrant? If it would have missed it, I should have moved, continuing my tree, until I either exit or end up in another triangle. So that's how quad tree helps us to do ray tracing. Just track the ray from one quadrant to another and go up and down in the tree in the obvious way. Once you exit one quadrant, it means you're entering one of the siblings of the quadrant. And if you have the hash table that we discussed earlier, even faster. But ray tracing happens in 3D. The triangle lives in 3D, so instead of quad tree, we are using, what's the name? Oct tree. oct for 8, right? Because we split by x, split by y, split by z. So we are ending up with 8 siblings. Okay. And we can generate, using quad trees, beautiful mesh generation. And these triangles are good for many different applications. If you want to send it to a CNC device, you want to run various simulation, you want to apply force because it's actually not a rigid body, and you want to see how it deforms when I apply force of it. Google for non-rigid body simulation in the SIGGRAPH community, and you'll see tons and tons of things. And how else do I use the quad? So let's say that these are a set of points that are points in a terrain. So P1, 2, 3, 4, 5 are points that live on a terrain. That's the y is elevation, and my quad tree is one-dimensional quad tree because I need to use slides for it. So the quad tree is just one-dimensional. The data points are 1 to 3 all the way to 7. And the elevation is some extra parameters that I set. Elevation above sea level. Why do I do the whole thing? Because I want to do flight simulation, and I want to use level of details. I know that there is, if that's elevation, because that's GIS data, that's part of a terrain that I got earlier, I want to generate it so I can render different pieces from here really, really fast. And if I can replace a bunch of triangles with one big triangles, I earn a lot of computing time. Bring us to level of details that we discussed last time. So if I can find a triangle that fits all the data points, all my elevation above sea levels just lies on a perfect plane, then surely I don't need to split it into a smaller triangles. But probably it's not the case. Mountains rarely are perfectly planar. So I'll decide an error level. And based on this error level that I can tolerate, how much is data points is further away from the relevant triangle that attempted to replace it, that would be my splitting triangle. Here, and I'm very much simplified it, I'll decide that if I'm trying to replace all these points, or to approximate the location of all these points by one single triangle, one segment in this one big case, the error that I get is more than the error that I allow. So following the quad tree philosophy, what do I do if I cannot fit all of them with one single triangle? I'll split, well, exactly in the middle. 1, 2, 3, 4 will go to one side, 5, 6, 7, 8 will go to the other side. Here are my two nodes that correspond to this quad tree. Here I represent it from 1 to 8 instead of 0 to 7. And now I'm trying to find one triangle that approximates what? Approximate only the points from 1, 2, 4. Just these points, and just approximate these ones. Approximate them with one triangle, and try to fit the points that approximate these ones. So we talked about storing some augmented data, 60 seconds, remember. We thought about that every node might store the number of data points inside its own subtree. That's cuter and much more useful part. Every node here will store the triangle, every node, not every leaf. Every node will store a triangle that approximate the data below it, the data it corresponds to. Again, every node will store one such triangle with the appropriate error, and I will not decide about the error ahead of time. We'll just compute it with each node, how far away, how good is one single triangle approximates all these points given the error. And now what I do in real time when I'm trying to render all of it, I start from the quad tree, and I'll see here is one such node. I know what is its range. maybe it's a huge area, but this huge area of the terrain is far, far away from the viewer, which says it's fine if there is a big error because the user will not notice. It's sub-pixel resolution, or it's small error, or it's not important level, or just that one triangle in this distance approximate good enough. Use the triangle that sits right here. Or if it's large area but the viewer moves closer and now suddenly one triangle is not good enough, then go to the two triangles and it's sub-children. And if needed, go to the triangles that in sub-children until you are down to individual pixels. Make sense? So the idea of level of details is something that we are using completely on the fly. As the viewer change their attention, focus, directions, distance to parameters, I'll use different approximation of this terrain as very tiny triangles if I'm very close to the surface, or much larger triangles, quads, if I'm very close, very far away from it, or that it's very flat. Here probably I'll use very small triangles because there is lots of changes, maybe, or I can use big ones if it's almost planar. I didn't argue that the whole triangle could be planar, but if I have something that is very zigzaggy, I probably need a lot of small triangles if I'm close to this region. Perfect. And again, I didn't speak about WebGL. But but do find out. I don't think that WebGL will do better job than. I have tons of self-confidence about explaining algorithms and data structures and approaches. I don't have tons of self-confidence about telling you that I'll explain WebGL better than you'll find other explanation on the web. So I'll do my best, but at the same time. Yak sec that I add the list of, on the other hand, sec Yuxul at Utah does fantastic job. Go check his YouTube. He has a course of Introduction to Computer Graphics in Utah that is available on YouTube, and it has a course. That's the last time that you're coming to this course because everything that he's explaining, it's much better than me, but definitely on WebGL. Go, even if you're using OpenGL, still go. And Explain has a course that uses OpenGL, actually, that uses OpenGL for interactive computer graphics. And he has a course of Introduction to Computer Graphics, where he uses WebGL. So, got it, whatever you want to use. Thank you.
Thank you.
What did we say the